In this video, we're going to tackle the topic of the conservation of energy. And this has been stated a couple different ways. And the first way we're just going to simply say is the total energy of a system must remain constant. Another way that a lot of times you'll hear this is energy cannot be created or destroyed. It can only change form. So what that kind of tells us is there's always going to be the same amount of energy in the universe. Now that brings into some ideas of entropy and useful energy versus non-useful energy. And now we work with fossil fuels a lot in our everyday lives, and there's a limited amount of fossil fuels. So it kind of tells us that there's still going to be energy left after we deplete the fossil fuels, but it's not going to be the same types of energy we had before. Another way of looking at this, if one object loses some energy, something else must gain the energy. And with fossil fuels, usually it's those energy of the car being used that is then given off to the outside environment as heat, which is a very unuseful energy if you don't want something to be warmed up, because it's hard to get that energy in some type of form that can be used with something else. So with that, we're going to kind of go from this idea to potential kinetic types of energy, and I've tried to apply that idea that energy cannot be created or destroyed. So here's our first kind of example with this. We have a basketball that's just simply sitting 2 meters above the ground. And the first question is, what speed does a basketball strike the floor with? So we know that this will have what we call potential energy, PE, or as IB would say it, EP, gravitational potential energy, which is equal to M times G times H. When this falls, it will gain kinetic energy. So on the way down, this will have some kinetic energy. Let's just say we're going at this point right here. But it will also have some potential energy. Now, we need to define a zero level when we're talking about potential energy. And in this case, it makes sense to say, you know what, this floor right here is 0 meters. Our potential energy in here is decreasing when we go back to this point. Our kinetic energy is increasing. So you have one energy type going up, but the other energy type's going down. We can figure out how much total energy was here by just simply saying, okay, 0.620, which is our mass, kilograms, times 9.80 meters per second squared, times 2 meters of height. That's going to give us a total of 12.152 joules. Now, when we get to here, if you total this up, it's going to also be 12.152 joules. If we go down to here, it's going to be the same idea. Our kinetic energy is going to continue to increase. Our potential energy is becoming less and less. But when we total that up, it's still 12.152 joules. When we get down to this bottom part here, at this point we have nothing but kinetic energy. We have no potential energy because we said H is equal to 0, which means all that energy now has been converted into total kinetic energy, which will equal 12.152 joules. So if we want to know the speed of this basketball now, we can go to the very bottom and say, okay, the kinetic energy, or again, as IB does it, EK, is equal to 1/2 mv squared, and just plug it in. 12.152 joules is equal to 1/2 times 0.62 kilograms times v squared. And when I solve this for v, my velocity is going to equal 6.3 meters per second. So by looking at a situation, this stuff in the middle was more just for explanation, understanding that our kinetic energy was increasing, our potential was decreasing. But we could have, at any point, if we knew what the height was, figure out its kinetic and potential energy, and then again go to its speed by doing that. But we just went to the very end at the zero level, which we can define to be anywhere we want to. We can define that zero level to be at the basketball. And then what we would find out is we are getting negative potential energy, but that negative potential energy will also give that speed. So the idea of where the zero is not that important. The best thing to do is to pick something that makes it easy on you. In this case, that's the lowest the ball is going to get. So say this is 0. Okay. A couple more examples, or one example that's got two parts to that with this, is if we took a roller coaster. And we said, all right, this roller coaster is going to start from rest and go down a hill that's 15 meters tall, and then go through a loop with a diameter of 8 meters. If we ignore the effects of friction, what is the speed at the point A and at point B? I'll just kind of go over here in red to make these a little more obvious. Again, we need to define some type of zero. And to me, the easiest thing is to say, all right, I'm going to make this 0 meters right here. And that's the lowest point. I didn't want to draw it right on top of here. This really shouldn't be moved up a little bit. So the lowest point is here. At this point, they're starting from rest, so we know there's no kinetic energy at all. The reason is because kinetic energy depends on velocity. So we only have potential energy here at the top. So to find a total energy, we can just say, all right, the potential energy is equal to mgh. And again, I use a different term or different symbolism for this. PE, EP is the same thing. We're stuck here a little bit. We don't have the mass. And that probably would be something that would be important, but this mass will always be different. If I have larger people in here versus smaller people, the mass of this cart won't be the same at all. But we do know the total energy should be the same. So now we have to think, okay, well, if I take this point as my starting point, and this point is my ending point, I have potential energy at the top, but no kinetic energy. Let me just kind of write this here. My initial kinetic and potential energy must equal my final potential plus kinetic energy. And then it's okay, well, what's going on with this? Well, we have no movement at the beginning because we stated that it started from rest. So that means this energy goes away, and we define this as my lowest point, so this energy goes away. So what it now says is, all right, my potential energy at the beginning will equal my kinetic energy at the end. Now I can start plugging in my numbers, or my formula, sorry. mgh is equal to 1/2 mv squared. And we notice mass is in both terms, which allows us to cancel it off. And I end up with just simply gh is equal to 1/2 v squared. Really makes the formula much simpler than what it was before because we just have one less variable. Plugging in our numbers, 9.8 meters per second squared is equal times 15 meters is equal to 1/2 velocity squared. So now the next step is just simply doing some algebra, getting these things combined in my like terms. I end up with 147 joules of energy. It would actually not be joules, I apologize. It would be meters squared time over velocity squared. But we'll just leave that off, I guess, to make things a little easier. Equal to v squared. My velocity at this point then turns out to be 17.1 meters per second. So we didn't need to know the mass in order to understand how fast that would be going around because the mass cancels off. And that's going to be pretty common for a lot of these type of problems. We still have to address point B. So again, without totally redoing this whole thing, we're still going to define this as our zero level. We could put it here. You know what, maybe what we'll do is we'll rework this afterwards just to kind of show you that one. So I'm going to clone this slide to my clone page, and we'll kind of come back to that idea later on of where the zero can be. But I want to know what my velocity is here. And the way we set it up, I will definitely have some kinetic energy because the velocity does not equal 0. That's what we're looking for. I will also have some potential energy because my height does not equal 0. This will still be the same. I still have no kinetic energy here because my velocity is equal to 0. So, going back to kind of the idea we had before, all right, KE plus PE initially is equal to my KEF plus my PEF. Doesn't matter what order you write that in. You know that this drops off. You know we have both of these. So, you know, and then, okay, mgh is equal to 1/2 mv squared plus mgh. And again, we can get rid of our mass because it's in every single term. So I'm going to end up with 9.8 meters per second squared times my height, which in this case will still be 15 meters, is equal to 1/2 times my velocity. Looking for that, don't know what it is, plus GH. In this case, is going to be 9.8 meters per second squared times 8 meters high. That's how high we are above the ground. So again, start plugging in our stuff. We end up 146.205, just to put all the numbers on there, is equal to 1/2 v squared plus 78.4 joules. So now we have to combine our like terms, and we're going to end up getting, you know, 67.805 is equal to 1/2 v squared. And then basically when you finally solve for this, my velocity is going to equal 11.6 meters per second. Remember, we're going to, I guess I should jump back a step. This is going to be v squared is equal to 135.61. But we need to take the square root of each side to get this v by itself. And then that takes us to this whole 11.6 meters per second. The idea being this is less than what we calculated before. We had 17.1. You know, if you kind of look down here, this is 17.1. The new speed is 11.6, which means we're not as low as what we were before. And that's our final speed there. If we go to another problem here now, this is one that we wanted to, you know, kind of revisit here with a new zero level. Hopefully that last one kind of made sense for you. What if we say this is 0? What if I just want to say where I end up is 0 meters? So I start here, I still only have potential energy. Here, I'm only going to have kinetic energy. Again, my potential energy is equal to 0 because my height was equal to 0. So, you know, how does that change things for us? Well, I still am going to have potential energy at the start, PE plus 0 is equal to my kinetic energy plus 0. Again, I have 0 kinetic energy here because my velocity is equal to 0, just like before. So again, mgh is equal to 1/2 mv squared. M's are going to cancel off just like before, so I'm going to get 9.8 times h, which in this case would be 7 meters. 15 minus 8 meters, that's 8 above the below, is equal to 7 meters. So again, that's just some traction. I'm sure it's not too big a deal. So 9.8 times 7 is going to be 68.6. That's going to equal the same 1/2 v squared. So if I just kind of carry my math out here, divided by 1/2, that gives me 137.2. is equal to v squared. Again, if I go back to the previous slide, I had 135.61, 137.2. They're very similar numbers. When I take the square root of that, my velocity is going to equal 11.7 when I use my sig figs. And again, 11.6, 11.7, very, very similar numbers. So it tells you that you can get about the same speed no matter where you choose your zero level. So those are some examples of conservation of energy problems.